I guess we can start. Everyone in? Yeah. Maybe you can close the door. Yeah. Okay, welcome everybody to this workshop, Prevention and Suppression in Large Car Parks. It's not quite a new topic, but there are some new developments, some new thinking, and maybe this is a nice topic to introduce you how to cope with project-specific fire safety concepts, in this case for car parks. I'm Ruud van Herpen. I am technical director at Niemann Consulting Engineers, but also one day a week I'm a fellow fire engineering at the University of Technology in Eindhoven. And that's called a kind of more practical professor, and also a professor at fire safety and buildings at the Saxion University of Applied Sciences. But in Eindhoven that's only one day a week, and this is half day a week. So I left. There's 3.5 days left for Niemann Consulting Engineers, and that's where I earn my money. So on the other. Before we start with the workshop, I think it would be nice to show you some questions, and maybe nice to see how we think about those questions. Oh yeah, okay, yeah. That's reacting a bit slow. I don't know if you are familiar with Kahoot as a site, and then you can play a kind of quiz in Kahoot. So on your mobile phone, you log into kahoot.it, and then you need a kind of PIN code. If you have logged into kahoot.it, you have to put in as a game pin 274257. So, and then I have 5 questions for you, and there is no wrong or right on that questions. Some answers may be more wrong or more right than other answers, but it's just to see how you think about fire safety in large car parks, and about fire scenarios, about thermal load, etc. You can give your own name, you can give a fake name, that doesn't matter because there is nothing to win. We have no points for the questions. Okay, well, still entering some persons. Yeah, okay, I guess everyone who wants has logged in. Oh, no. Okay, well, Marco, Joost. Okay, well, we start. 5 questions about fire safety of car parks. The first question, what is, do you think, the definition of an open car park? Is that a car park without external separation constructions, or without a roof or ceiling, or with no accumulation of smoke, or no accumulation of heat? And maybe several answers are good, that are correct, that's possible. But I'm curious about how you think about the definition of an open car park. Yeah, each question gives you 30 seconds, so you have to decide quite quickly. Okay, well, most of you think, and that's not strange to think about the solution, no external separation constructions, because they are very much related to each other. No external separation constructions means also no accumulation of heat, of course, and maybe no accumulation of smoke. I think my answer would be no accumulation of heat, because if we don't have accumulation of heat, then then we can create boundary conditions that prevent a developing fire to develop to a flashover. So then we keep a localized fire, and that is much like a fire in the outdoor. Then an indoor fire is different from an outdoor fire because flashover could happen. If you can prevent flashover, well, that could be a definition of an open car park. If you think about no accumulation of smoke, then you are thinking about personal safety, I guess. And well, that's also a good reason for a definition of an open car park. But then it's not the definition of the developing of a fire. No, then you are thinking about personal safety and inhalation of smoke and visibility, etc. Okay. Next question. What are possible fire scenarios in closed car parks? Closed car parks, so a car park like this. Is that a localized fire, so a small fire, several cars, or is it a traveling fire? That's a localized traveling fire, I mean, in that case. Or is it a compartment fire? And you see here a kind of underground car park, I think, made of concrete, so it's a thermal heavy construction. Okay, you already all answered. Very fast. Most of you think a traveling fire. Well, I think that might be the right conclusion. But if you don't have any measures at all, I think it's possible that a developing fire in a closed car park develops towards a flashover, and then you get a post-flashover situation. So if you assuming a traveling fire, that means that you think that in case of a fire and a traveling fire, that may cost a lot of time. in that case, that the flashover conditions in the parking won't be reached. So that means that you have to do something about that. You have to do something about keeping the temperature sufficient low for low radiation and low convective heat transport to prevent flashover. So this is possible, but I think it's possible in combination with a lot of accumulation, so a thermal heavy car park, and certain ventilation conditions. And a localized fire is only possible if you can put out a fire. So then we are thinking about the sprinklered fire, automatic suppression, or manual suppression by the fire brigade. But manual suppression by the fire brigade means that you have to create conditions for the fire brigade to put out a fire, and that's much more difficult than conditions for a traveling fire, because you have to reach the fire. Oh, sorry. Okay, scoreboard, but that's of no importance, as you see, because there were no points to gain. What are possible fire scenarios in open car parks? So the same question, but now, oh yeah. Well, it's coming back, I know that, but okay. Maybe, yeah, I don't know if I can, well, let's see if you can make it in time. It's the same question, but then in an open car park like this. Well, what type of fire do you expect in that car park? Yeah, well, not everyone answered, I think, because we had a black screen in between, but okay. Well, this will be definitely a wrong answer, compartment fire, because it's an open car park. And an open car park means that a compartment fire isn't possible. So, luckily, no one took that answer. It can be a traveling fire, because it might be not possible to do an offensive attack, because you cannot reach the fire. Also in an open car park, it's possible that the smoke spread all over that parking level. So that means that that maybe you cannot do an offensive attack, and that means that we get a traveling fire. Sometimes localized fire might be possible when you have a low rate of heat release scenario, or when there is enough wind and well, a good wind direction. So that means that that the smoke isn't spread all over that level, but is away in one direction. Yeah, okay.
Sorry.
So this means offensive fire attack or a sprinkler installation, automatic suppression. So that means special measures. Without special measures, I think traveling fire is the most likely scenario in an open car park. Again, scoreboard. What fire scenario implicates the most severe thermal load on constructions? Well, then that's here you see the same scenarios, but then in the localized fire, I made the difference between manual suppression and automatic suppression, compartment fire, traveling fire. Well, I'm curious about your answers. Time up. Not everyone managed that in time. Yeah, most of you think the compartment fire, and I think I agree on that. That the compartment fire is the most severe thermal load, not only when it comes to temperature and duration of the fire, but also because a large part of the construction is exposed to that thermal load. When you have to deal with a traveling fire or a localized fire, then only a small part of the construction is exposed to that thermal load. And that means that also the failure probability is much lower than when it's a large part of the load-bearing elements. So I agree on that I think the compartment fire is the most severe thermal load. Oh, again, scoreboard. The last question, what type of cars implicates the most severe fire scenario? The fire scenario is important because the rate of heat release, that's basically the engine of the temperature development in the compartment. Is it normal petrol diesel cars, electrical cars, hydrogen cars or LPG cars? And, well, there are of course maybe some more types. I think this is a difficult question to answer. I find it a difficult question to answer, at least. You see, I think we have to wait a few seconds. You see, I think, well, I really don't know. So every answer is the right answer. Because we don't know how future cars are. If we are going to drive all electrical, yeah, you know, we know? Yeah.
That's not officially published yet, but from the research you could conclude, and there are 4 tests on 2 types of these cars.
Yeah.
That the modern cars, electric, hydrogen, and LNG,
yeah,
are not more severe than the old.
Okay. Okay.
Cars.
Okay. Well.
It's only more difficult.
That's hopeful. That's hopeful. Yeah.
So that this morning.
Yeah. 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 Yeah, yeah, because what we saw this morning, I really don't know what's the most severe scenario. But if there are tests, but not published yet, and those tests shows that electrical cars, hydrogen cars, and LNG cars are not more severe on fire scenario than the normal petrol and diesel cars. Well, I think that's hopeful because then maybe we are now calculating conservative. That would be nice. That would be nice. Yeah. So you are very divided, and that's for me too. I really don't know, because if it's only when we think, well, petrol and diesel cars are gives the most severe thermal load, then we still don't know how the development in the future will be. We don't know how many plastics, how will car development, how will car design will be in the future. So. There will always be a lot of uncertainty in the rate of heat release scenario. Okay, well, I think I can give a summary of the answers for if you like, but then we will upload that together with the handouts of the workshop. So I can go back to that presentation now. Okay, I don't know why Jeffrey is here shown, but maybe he's the winner. Yeah. Yeah. Okay. Well, I also have the presentation on my laptop, but you see the problem of an external laptop is that the screen. Okay, here it is. Here it is. Okay, I can skip some slides now, because these were the slides that we did in Kahoot, the questions. So here I am. Okay, maybe it's good to realize that in Holland and in most building acts or fire acts or however they're called, there are only two main goals, main objectives: personal safety and safety of neighboring plots. And also Luke told us this morning when he talked about fire resilience instead of fire resistance. And he said also, well, in most building acts, personal safety and safety of neighboring plots, that's what counts. So we don't care about safety of our own building, we don't care about property protection, we don't care about sustainability, etc. That's true, and in the Netherlands and in most countries, the objectives of the Building Act are made more concrete in the building code. And in our Dutch building code, you see some prescriptions are very much related to those two main objectives. Safety of neighboring plots, you find in the building code, safety of escape routes and safety of attack routes. But then you see also prescriptions that have to do with the safety of the building structure and safety of fire and smoke spread, compartmentation and subcompartmentation. And you can think about, well, compartmentation, what has that to do with personal safety? Or what does it have anything to do with safety of the neighboring plots? Well, maybe not directly, but you can see that as a kind of line of defense, as it takes more time before a fire develops to a building fire. Then you have more time for personal safety. Then it takes more time before the neighboring plots has a flashover risk. So you can see that as a line of defense, and that's not only for separation constructions, because separation constructions are related to compartmentation, but also for load-bearing elements for building structure. And those lines of defense, well, a popular risk model for evaluating those lines of defense is the cascade model. This cascade model, and this cascade model is basically that every step you decide what is the probability of fire developing to the next step, or what's the probability that the fire stops. So this is the origin of the fire. You see the fire triangle, the development to a local fire, a localized fire, the development to a compartment fire, and the development to a building fire. And this fits very well for separation constructions, for compartmentation. It's a model that works very well. For load-bearing elements, it's a bit more complicated. When the thermal load on load-bearing elements is that high that the structure collapses. If the structure collapses, then well, you have basically you have then a building fire. Then the total building is on fire, because then the separation construction well, are not stable anymore. So load-bearing elements, the building structure, means basically that if there is a collapse, then we have a building fire, and well, we have to see if that situation is acceptable. Maybe that's why you see that the requirements on load-bearing elements are more severe than the requirements on separation constructions in the building code. Oh, I have to do this. with this cascade model, with these objectives of the building code, it doesn't work to fill them in with the standard fire curve, because the standard fire curve has nothing to do with a real fire. It's a kind of temperature development in time, well, that's okay for a test method, but that has nothing to do with the real temperature development in case of fire. So we have to do that in a more realistic way, and that's a natural fire concept. The natural fire concept means that you take a look at the fire, but also at the building, and especially at the interaction between fire and building. And then you see that when a fire is developing, at a certain point you reach conditions in the compartment or in the building that leads to flashover. And well, the moment of flashover is a typical example for combination of fire characteristics with the building characteristics. And you see that also in, I have to go back, is that possible? No. You saw it also in the cascade model that, well, and you also answered that on the questions, that the main thermal load, the most, is in the post-flashover situation. So the localized pre-flashover fire that hasn't a severe thermal load. The severe thermal load is after flashover. So that's a very important incident, and maybe good to realize that the building code assumes a compartment fire and says, well, if there is a compartment fire, then I have to realize safe escape routes, safe attack routes, safe compartmentation, safe building structure, but all with the boundary condition of a building, of a compartment fire. So if you can prevent flashover, then you have well, a thermal load that is not very significant, and maybe you can you don't need or need any more fire-resistant load-bearing elements, or fire-resistant separation constructions, or maybe at a lower level. That might be possible because the thermal load is much lower. Oké, even kijken. Maybe this? No. I don't know what I did now. But this doesn't. Okay, I already told you that prescriptive rules of the building code are assuming a compartment fire and then limiting the maximum consequences. So it's control of effect, control of consequences, and we don't do anything or not very much about the probability. It's only about controlling the effect. Well, besides compartment characteristics and fire characteristics, of course there are also human characteristics important because, well, the physiological effects on skin, on inhalation of smoke, etc., but also about organization. How do we get, that's especially important for personal safety. I think you understand that, and well, this, maybe you have seen this figure before. This is a popular picture for well, showing what fire safety engineering is, that we have to do with three kinds of boundary conditions that are important for a project-specific solution. Oh, I have to do this. Okay, then we go to the car parks. Well, a car park is maybe a very simple building construction, very simple building, but what we know in the building is the fire scenario, or more or less we know the fire scenario. And that means that this building type is especially suitable for fire safety engineering, because if you can define the natural fire, then you can engineer safety in a proper way. I did well, long ago I made a fire safety concept for Netcar. That was in 1995 in Borne. Borne? Yeah. And then they made, in that time you had the Volvo 440, 460, 480, very old type, but then that was the standard mid-class car. And because they were assembling that type of car, they knew exactly what materials were in that car. So I could exactly establish the fire load of one car. So this is a kind of a mean value of the Volvo 440, 460, 480 as the fire load for one car, 10,000 megajoules. And that's not the fire load that we calculate when it comes to the fire scenario of a car. Because if we take a look, and that is the next slide, at the rate of heat release scenario, you see that the total fire load is less than 10,000 megajoules, approximately 6,700 megajoules. So that means that we have an efficiency of combustion of 67%. So that's not a very high efficiency, but okay, maybe. So you can ask for yourself: is this a conservative assumption? I'm not sure about that. Fire duration approximately 40 minutes, and the mass optical density, so smoke production of 400 square meters per kilogram. And to make a comparison with normal building fires, in normal building fires we assume a smoke production, a mass optical density of approximately 100 square meter per kilogram. So this is 4 times higher. But, well, I think you can imagine why that is 4 times higher. That's because of the use of plastics and the tires of the cars that produce a lot of black smoke. Okay, as I already mentioned, here you see the rate of heat release scenario for one car. This is from CAPAFI, European that stands for car park fire, European research for fire development, natural fire development in car parks. And this is the rate of heat release curve from one car. So let's say that is this car, the first car. And then you see ignition of the other cars, the adjacent cars, with a constant time interval with the same, more or less the same scenario. The fire load of one car is, let's say, the surface that's beneath that curve. So with this rate of heat release curve, we have a fire load of, you saw it on the former sheet, 6,700 megajoules. So that's less than the 10,000 megajoules. And the 40 minutes durance is, well, about after 40 minutes you see a kind of smoldering phase that is not of very much significance anymore. So you see ignition of car 2, of car 3, of car 3 with constant time interval. And, well, if you don't put out the fire, then it won't be 4 cars, but that may be a complete row of cars that will set on fire, car after car. And well, I can summarize those scenarios, and that's what I've done in this curve. It's basically the summarization of all those separate scenarios. And well, the dotted line, that's basically the global line, the rate of heat release that you get in this case by what you get here is a kind of a traveling fire. So we see that car 1 is finished after 40 minutes, and well, then at that moment we have 4 cars on fire, 4, maybe already the 5th car, and that means that we have a more or less constant fire size of approximately 4 or 5 cars, and it's moving through the row of parked cars, but more or less constant in size. And the constant size you see here in the rate of heat release. After approximately 60 minutes, we have a constant rate of heat release. And it's a rather high rate of heat release, approximately 18.5, 19 megawatts. But that's the rate of heat release of a traveling fire. Yeah. I'm going back now. That's not good. Yeah. What's the problem with that? Okay. I don't know. Is it the next sheet, or I'm already 5 sheets ahead now? I don't know. Is it really the next sheet? Yeah, I think so. Yeah, this okay. Yeah. Okay, so I have an example to show what that rate of heat release, what the consequences are for different types of car parks. And the geometry is very simple of the car park. It's a rectangle plan and a constant height. No wind influences, ambient temperature, constant level. No fire suppression. No fire suppression means that we follow the natural fire concept. So it's only fire and building that is of importance. There's no suppression. Well, I took 2 conditions: an adiabatic condition, that means a very light construction, very good insulated, and compared to a very heavy construction with no insulation. And also 2 types of ventilation, an open car park compared to a closed car park. We did that with simple zone modeling. So of course that's a very simple approach, but I come to some special localized effects later. This is an open car park. This is car park Jette in Brussels. And that's basically a floor and a floor, and you see no facades, so no external separation construction, or maybe 90% open. Concrete floors, natural fire development. First question, flashover or not? Well, that's the question we already answered in the beginning. So we don't expect any flashover here because the car park is too open. You see here the graph, the outcome of the zone model. This is a time axis, 3600 seconds. This is 1 hour. This is 1.5 hours. And the rate of heat release is on this axis. So that's this line. That's the rate of heat release. That's the same line that you already saw. That's the rate of heat release of the traveling fire scenario. And the gas temperature is this line, and that's on the left axis. So you see that the maximum gas temperature is about 68, something like that, 68 degrees Celsius. So that's rather a low temperature. It's not a temperature for igniting all the cars. So we are far before flashover conditions. There is no risk of flashover. So if there is no influence from the outside, you may expect in this case a traveling fire. Then you can ask yourself, well, is it possible in an open car park to do an offensive fire attack? That means that we approach the fire and put out the fire. The fire brigade does in that case. Well, here you see the more or less same graph, in the first hour in this case, and this is the temperature. That's the same as you saw in the graph before. Well, it's now on Kelvin, but that's okay. The same temperature, and I added the visibility line. That is this line, and this is related to the right axis. And you see that, well, in the beginning there is some visibility, but it's very rapidly decreasing, and to a visibility approximately, well, 2 meters, something like that. So a visibility of 2 meters, we assume in this case homogeneous mixing. So maybe that's a bit conservative. I'm not sure about that if it's conservative, but you might think it's conservative. A visibility of 2 meters means that an offensive attack in the parking itself is not possible, because you can't see the fire. You can't reach the fire, you can't approach the fire. So that means that a localized fire scenario, an open car park, in many cases, I think, you should, I think that is a bit too optimistic. I think it's a traveling localized fire that's more probable than a local fire that can be put out by the fire brigade.
But is that without systems included?
Yeah.
Results without systems included?
Yeah, this is only the fire and the building construction. So there is no fire brigade and there is no sprinkler installation, there is no smoke ventilation, nothing. It's all natural. And you see, if you think, well, in that very simple parking, is it possible to do an offensive attack to put out a fire? Not in this scenario, because the visibility is too low. Of course, there are also scenarios. This is only a design scenario. That means that it's not always this scenario for the fire. It might be a lighter scenario, it might be a more severe scenario. In lighter scenarios, it may be possible to do an offensive attack. So it's not that we always have the same fire tactics, because every time we don't have every time the same fire. That's the problem in this case. But we are very much thinking in only one concept. We are very much thinking in a parking that might be where we reckon on an offensive fire attack, when we do always that offensive fire attack. It's not always possible. Because if there is wind and the wind is from the right direction, it might be possible to do an offensive attack. You don't know what the boundary conditions are, and you are depending on the boundary conditions if you can do an offensive attack or not. The same fire, but now in a different car park. In this case, a closed car park, underground car park, a thermal heavy construction. That means that the construction that the gas mass in the parking cools down to the construction, and kind of basic ventilation, mechanical exhaust of 30 cubic meters per second. That means 10 times ventilation, 10 times per hour. This is rather rather heavy ventilation system, and also a natural fire development. Here the same question, the first question, flashover or not in this case? Well, here we were more divided. Some of you think flashover is possible, some of you think, well, I don't know, I think traveling fire. Well, let's see, with zone modeling. You see here, what do you see here? Oh yeah, temperature. Okay, temperature. It's the same fire scenario, the same rate of heat release scenario. Here you see the temperature development, this line, and the temperature is on the left axis. Well, in this case, after 90 minutes, I'm at a temperature level of 128 degrees, something like that. So that's a bit higher than the natural ventilated car park, than the open car park. But still, it's not flashover conditions. So that means with this ventilation, 10 times per hour ventilations, we don't reach flashover conditions, and a traveling fire is a most probable fire scenario. Visibility, however, in this case, well, is even lower than in the open car park. It's about 40 centimeters, 0.4 meter. So in this closed car park, to do an offensive fire attack is almost, with this scenario, is almost impossible.
Ruud, in both cases, the assumption is that that the traveling fire is one car after another. Eh?
Yeah.
And we both know that's not true.
Why?
Because cars move and are happening all
That's
kinds of
possible,
things.
yeah. Not every car is moving when it's on fire.
No, but
That's possible. Yeah. Just like the fuel on the floor, that's also possible. So it's a design scenario. It's what we call a design scenario. So it's the real scenario is never exactly the design scenario. Sometimes it's lighter than and sometimes it's heavier than the design scenario. You're right about that. Yeah. So this is indeed the assumption that one car after another is ignited, and that we have in totally 4 or 5 cars at the same time on fire. So you see, it's well a bit worse than the open car park, but still, this is most likely a traveling fire, and we don't reach the flashover conditions. Here I have the same car park with the same ventilation conditions, but in this case, not a concrete car park, but let's say a car park, if that would be possible, completed, assembled from, stone wool, something like that. So a very lightweight construction with a very high insulation. We call that an adiabatic calculation. That means that all the energy remains in the gas mass. So that's a very conservative assumption. And you see with that conservative assumption that the temperatures will rise enormous. And in this case, well, let's say that flashover is probable after, in this range, 300 to 500 degrees Celsius. That's already after a quarter of an hour. So, yeah, with the assumption of an adiabatic construction, it's not only a poor visibility, there is also flashover risk. And that's good to realize that the flashover risk is not only depending on the rate of heat release and on the ventilation scenario, it's also depending on the construction, on separation, especially separation constructions. Are they thermal heavy? Are they thermal light? Are they insulated or not? Because if I have a thermal heavy car park, a concrete car park, but insulated with stone wool at the side of the car park, then it's basically an adiabatic construction. And then certainly there is risk of flashover. So you see that there are a lot of boundary conditions that are related to the fire scenario, and you don't know all that boundary conditions, and you cannot anticipate on all those boundary conditions. So you have to take into account several scenarios, not only one scenario, but several scenarios. An offensive fire attack, let's say a kind of summary is this slide, is possible when I have, I can do that automatic with kind of sprinkler or automatic fire suppression installation. I can do that by hand, manual, with the fire brigade, but then I need to realize conditions in the car park that are suitable for an offensive fire attack. That means that I have to do something about smoke control, and that means that I have to do more than only realizing sufficient ventilation. No, I also need to get rid of the smoke in a certain direction. So I have to create a smoke-free area in the car park or in that level for the offensive attack from the fire brigade. And if that's not possible, then we go to a defensive fire attack. That means no direct suppression. We come to a localized traveling fire if we can create boundary conditions in the car park to prevent flashover. So then we realize a localized traveling fire. If that's not possible, then we get the last scenario. That's a compartment fire, and that's basically the scenario that fits best in the building code. That means that we have to realize also the measures according to the building code. That means 1,000 square meter compartment area, 60 minutes fire resistant, etc. As I already told, there are a lot of uncertainties. Uncertainties in rate of heat release scenario. What kind of car? Rolf already said, well, maybe that's an uncertainty that's not, maybe if we know that petrol and diesel engines are, if that rate of heat release scenario is the most severe scenario, okay, then this uncertainty is less significant, but still there is a lot of uncertainty in rate of heat release scenario. Also in smoke production, the mass optical density might be much higher in the future than now. Also about the calculations that we did with the zone model, because in that zone model we are talking about homogeneous mixed zones. And that means that we don't take into account local influences. Yeah, well, how can we realize a robust fire safety concept? We can only realize a robust fire safety concept if we can do, if we can, with the sensitivity analysis, if it's not very sensitive for those stochastic boundary conditions, those boundary conditions with uncertainties. So basically you have to do a sensitivity analysis to see if your fire safety concept, if that is a robust concept. Well, this is, yeah. Okay, this is only a kind of, what you see here is well, starting a car fire at this place and then developing in both directions to other cars. And the circle gives the rate of heat release, and so that's, so you have well, so you have kind of what's happening and well, you can imagine that this is well, depending on the cars that are parked adjacent to each other, one to each other. The local thermal load depends on the distance on the fire axis. If here this is the fire start and this will be a beam above that car, then it's exactly in the fire axis. So that beam will have the highest thermal load. And you see that with the traveling fire, the local thermal load will decrease because the fire is moving away from the center of that beam. So the local thermal load is of course maybe very, very high, but it's not that high as a compartment fire because the time of duration, the time of the thermal load is much shorter than in a compartment fire. And it's only one element in this case. Well, of course, there may be another element and another element, and well, that's the difficulty with a traveling fire, that more than one element is exposed to that local thermal load. And it means that also the risk of collapse, the risk of failure, is higher than when it's only one element of the load-bearing structure. Well, you see a comparison of the localized thermal load with a sprinklered fire, this line. A localized fire, that means that a localized fire only at a fixed location, 3 cars, and then the fire brigade put out the fire. So that means a successful offensive fire attack. And this scenario, a localized scenario of a traveling fire, that's basically the same scenario as you have seen before. So that's developing in this way much longer. But you see, well, of course, in rate of heat release it's developing, but it's also moving away. So when the distance is 3-4 cars, then the influence of the localized fire is of no significance anymore. And that's why for the traveling fire, I draw this dotted line as a thermal load. So that's the thermal load of 3 localized fire scenarios. And here you see the thermal load of on one element of a traveling fire. So basically this is the rate of heat release scenario in total for the traveling fire related to the right axis. And here you see the temperature axis, and this is the global temperature, the temperature of the mixed zone. So that's, well, approximately 68, 70 degrees, the value that we have already seen before. And here you see the temperature caused by the localized fire at one element, one beam or one column that's in this case in the fire axis. And you see that that might be very high temperatures, but not for a very long time. So still there is a possibility to realize a robust fire concept, or realize fire-resistant load-bearing elements with well, another fire resistance than according to the building code. And that's because of, well, the thermal load in this case, another thermal load than according to the building code from the traveling fire. Okay, when we can make sure that by automatic suppression or manual suppression by the fire brigade, that we have to deal with a localized fire, then the thermal load on elements is not only the lowest thermal load, but it's only related to one or very small part of the load-bearing structure. When there is no suppression and we have to deal with a traveling fire, and then you see an increasing of the thermal load, but also an increasing of the part of the load-bearing structure that's exposed to that thermal load. And that means that well, we have an increasing failure probability from the load-bearing elements, especially when it's a large part of the structure. Then there is then you cannot take into account any redundancy anymore. Well, how do we deal with that? Well, you can deal with that by decreasing acceptable failure probability per element with a probabilistic analysis, or by, well, a method that's applying a risk factor on the rate of heat release, a method that's also related to the Eurocode, because in the Eurocode we do more or less the same. We apply a factor, a risk factor or a safety factor on the rate of heat release, or on, in Europe, basically on the thermal load. In Holland we do that on the rate of heat release. It's not quite the same, it's slightly different. That means that the decreasing acceptable failure probability is how do you say it? It's taken into account in realizing, or in taking into account a higher rate of heat release.
May I ask a question?
Yeah.
On that last one, because you say you use the
on the former slide.
You use the approach in the Eurocode on the risk factor on the rate of heat release.
Yeah.
But that is a risk factor that is for the
Postless overfire.
magnitude of the compartment.
Yeah.
But it is for compartment fires.
Yeah.
It's developed for compartment fires.
Yeah.
It is also a probabilistic method. What you do here for carparks is not probabilistic. It is a scenario you put anywhere in the car park.
Yeah.
Is it? Can you apply this method also for
Well,
this kind of fires?
I agree with you. That's discussable if that's possible, because the compartment fires is a probabilistic method also for the thermal load, and I'm not sure about, for instance, the kappa phi method that's developed in the same time as the natural fire concept for normal compartments. If that's only based on a few experiments, so I think you cannot say that's a probabilistic method. That's what you say too. Okay, yeah. So if that, I agree that but the technique of applying a risk factor might be a good technique also for a localized fire. But if it's exactly the same as in the Eurocode, I agree with you. That's not possible. No. Maybe an own probabilistic analysis, a sensitivity analysis on boundary conditions would be a better method, but it's more complicated and takes more time. So this is what related to the Eurocode, and well, the only thing, it's not quite the risk factor according to the Eurocode. The only thing that I did in this case was when it's a localized fire and we have this rate of heat release scenario, when it's, instead of a localized fire, it's passing 5 columns and 5 beams instead of 1, then we use the same multiplying factor as in the Eurocodes, and that, well, then I established that this is the risk factor, and for 10 elements this will be the risk factor. Okay, I think that the method still is suitable also for a localized fire, but I think it's not validated yet for that localized fire. So that's a difficulty, and If it's not validated, maybe you should make your own probabilistic approach. But that, as I said, is a lot of work, because then you have to do a sensitivity analysis on all stochastic boundary conditions separate, and well, that's a lot of work. But that localized fire are important. Traveling fires are important for structural collapse, but or not only for load-bearing elements, also for separation construction, because I think most of you recognize these pictures from the car park Lloydspier, Rotterdam, where well, you see here concrete floors that are well, damaged in a severe way. So that means that we have a very high repair cost to realize here a new floor. So there are several constructions are very sensitive for that high localized thermal load. And well, steel structures are sensitive for high thermal loads, but also concrete structures, in this case special concrete floors. Wooden structures, we already talked about that this morning, because then they're also burning. It's not only a structure, but it's also a structure that's burning, part of the fire load, you could say. So the localized fire is very important. I don't know to what time can we continue?
Almost. You have a clock left, about 20 minutes.
20 minutes left. Okay. Okay. Well, you're very quiet. Well, maybe. You
don't want to interrupt you, but you can say I hear very often at night.
Yeah.
And, you assume a lot.
Yeah.
But how can you explain that by coming to the risk?
Yeah.
Because
yeah. Yeah. Well, if you have to make a lot of assumptions, or if you have a large uncertainty on your boundary conditions, you can still calculate with fire safety engineering techniques the risk. But if the uncertainty is large, then for instance, when it comes to load-bearing elements, to the structure, you want to know if the thermal load, or if the structure can withstand the thermal load. If there is a lot of uncertainty in boundary conditions, then you need a larger interval between the source and the response. That means that instead of, for instance, 45 or 60 minutes fire resistance, you need 60 or 90 minutes fire resistance. So that's calculating with uncertainties. It's possible, but the larger uncertainties are, or the more uncertainties, the larger the interval is. And that means that it's you can calculate you can simulate fire safety engineering the best if you know the boundary conditions very well. Then it makes sense in any case. But then you can calculate most accurate if you know the boundary conditions very well. So that's a problem that we all have to deal with, and that the other problem is that you are that these kind of fire concepts that you make are project-specific solutions, and that means that if something is different in that building in the future, the fire safety concept may not be suitable anymore. So that's also a problem when you think about sustainability, about flexibility in the future. The concept needs some room needs some flexibility for future use, and you see also in the rate of heat release that is boundary. Even for the cars now, we don't exactly know the rate of heat release in the rate of heat release scenario. So for future cars, that will be more difficult. And the more we anticipate on the rate of heat release that we know for cars now, that means that if the rate of heat release in the future will be different, it might be the case that car park is not suitable to use as a car park anymore, but only for bicycles or something like that. So that's the difficulty with project-specific solutions. That the boundary conditions you don't know for sure, and especially the future conditions are difficult to forecast. That's difficult. Are there other questions? Because if not, I can try in 15 minutes to show you an example. An example of an existing car park, and to do a kind of review of the fire safety level in that existing car park. This is a car park in Amsterdam, under a residential building. So it's only for residential use, and it's not very large. You see the plan of the car park. It's an underground car park with one entrance, that's here, and it's a mechanical ventilation system, mechanical exhaust system. You see a ventilation shaft. Ventilation, I thought the ventilation was 10 times per hour, so there was rather kind of fire ventilation. And well, that's it. I think it's approximately 2,000 square meters, something like that. The escape routes at these places, and I don't know exactly what these are, but there are other compartments like I don't know. Other function than a car park function, because if you make fire safety concept for a car park, and that's related to the rate of release of a car fire, then only cars are allowed in that compartment. So if you have, well, bicycles, it may be not quite a problem, but if you have other fire load, that's basically not allowed in that compartment, because then you have another fire scenario. Okay, it's a concrete building structure. We don't know exactly the fire resistance because it's an existing building, and I think that I'm not quite sure if it's an estimation or that we know if this is the level that is really available there. For load-bearing elements, fire resistance of the load-bearing structure, 60 minutes, and the fire resistance of separation construction, in this case the floor to the residential function above the parking, of 30 minutes. This is an existing building. That means that the acceptable compartment area is 2,000 square meters, and here we find that there is a fire ventilation 10 times per hour to support offensive fire attack. So apparently offensive fire attack was one of the assumptions for this car park. But as we know already, with 10 times per hour, that's not enough. You didn't see any thrust ventilation in the car park, only mechanical exhaust at one point. So we don't know much about the spread of smoke. So that means that 10 times per hour is not enough to support offensive fire attack. So that's why I'm not sure if this is a realistic assumption, but that's why I thought, well, offensive fire attack is not the only relevant scenario. I think the other relevant scenario is the traveling fire in this car park, or maybe even a compartment fire. But I think with 10 times per hour, compartment fire is not very realistic. So that are the two scenarios that we think are most likely in this case. Here you see the four scenarios: compartment fire, traveling fire, localized fire, and the small localized fire, let's say the sprinklered fire. Well, then you think, oh, why 430 square meters? Well, in the traveling fire, if traveling fire happens in this center area, then I don't know exactly how many cars, but then this is the most severe scenario, more severe than a scenario here at the facade, because this is the largest area. So for the traveling fire, we took that this will be the total damaged area in case of fire. And that's approximately 430 square meters. A local fire has only 3 cars, 3 places, so that's a very small area. And a sprinkled fire, only 1 car, 12 square meters. Compartment fire, compartment, I don't know exactly this compartment, but I think approximately 2,000 square meters, maybe a bit smaller, I'm not sure about that. But, well, the probability of that is 0, so there is no, I didn't fill in the compartment area. So these are the 2 most probable scenarios, traveling fire and localized fire. And what I did was try to define a risk factor and translate the risk factor in a thermal load according to the standard fire curve. That's something Luke also mentioned this morning. He showed you a graph with the surface underneath a natural fire temperature compared to the standard fire temperature. And he said, well, if the surface is equal, then we can say that the natural fire has a certain time of standard fire, then we're talking about the same amount of energy. Because basically it was an energy equivalent. So I did that here too, and well, oh, I have to do that here. Maybe I have to give you some information about some research that we did already some years ago for the Dutch Standardization Organization, that's NEN, to link the Eurocodes to our building code. Because Eurocodes is thinking in constraint classes and failure probabilities, acceptable failure probabilities. And our building code is not thinking in failure probabilities, but is thinking in minutes fire resistance, minutes according to the standard fire curve. So here you see the same problem, how to connect a failure probability related to a fire safety engineering solution with a natural fire concept. How do we relate that failure probability with minutes according to the standard fire curve? And well, we found, well, it's not quite real. It's basically a kind of an assumption, but also we think that the assumption is conservative enough that when we say 60 minutes fire load, that's more or less the normal level. That means a risk factor of 1. Then if the fire load is doubled, 120 minutes, then we have a risk factor 10 times higher. Or in this graph, it's not fire load and risk factor, but here it's fire resistance and safety factor, but basically the same relationship. Fire resistance of 60 minutes means safety factor 1. Fire resistance of 120 minutes means safety factor 10. That means that the failure probability is, in this case, 10 times lower than in a 60 minutes fire resistant construction. That's basically the meaning of this graph. So, to do it here. So that means that the risk factor, maybe I have to show it here, risk factor of 0.12, it means a probabilistic thermal load in minutes standard fire curve of 31 minutes. So that, therefore we use that graph. And we compared that, I can better show the graph thing, I think. I compared that with the requirements for existing buildings according to our building code and the requirements for new buildings according to our building code. And here you see the requirements according to the natural fire concept for the parking that I showed you, the car park that I showed. The first column is the separation constructions, and the next 2 columns are the load-bearing elements in 2 classes. A standard class, that means normal buildings, and high risk for residential buildings, higher level for residential buildings. For residential buildings we have for the higher level for a certain height in Holland, 120 minutes fire resistance of load-bearing elements. And for existing buildings only 60 minutes. So you see that according to the thermal load according to the natural fire concept, well, gives in this case requirements that are a bit higher than the requirements for existing buildings, but not that high as required for new buildings. So we had here an estimated resistance of the load-bearing elements of 60 minutes. Well, I need a bit more than 60 minutes, but it's, well, very, very much in the range. And for the separation construction, 30 minutes. Well, here, I don't know exactly, but oh yeah, it was 31 minutes. So that's comparable to the 30 minutes that is that is needed in this case. So for this car park, the conclusion was, well, there is no urgent need to do something about, although the fire concept is totally different than was assumed in the design of this car park. It assumed was an offensive fire attack. Well, we think it's not always possible, and maybe you should say. Because we thought, well, 50% traveling fire, 50% localized fire. Maybe you should say 100% traveling fire. Maybe that's more conservative, of course. You can try that too. But maybe that means that in this graph, the columns will be slightly higher, but not very much higher, slightly higher. That means, although the concept is totally different than the original concept, there is still no urgent need to do something about the load-bearing elements and separation constructions of this car park. Of course, there are also other conclusions for other car parks. So this is only one example. But that's how you can can evaluate existing car parks, taking into account the fire scenarios and also related to that fire scenarios, the attack scenarios from the fire brigade. Okay, so that was only an example, and I think that this, yeah, I skipped this because this is new. This gives new discussion, and okay, we leave that. I stick to this. So this was the area, the area of traveling fire. For that traveling fire, we need a ventilation of 10 times per hour of the volume of the car park, and then a fire resistance of load-bearing elements of approximately 60 minutes, slightly more, 62, 63, I don't know exactly, and 30 minutes for the floor, the separation construction. But then, of course, related to a traveling fire scenario, a car fire scenario. So sometimes you see that the ceiling of a car park isn't of concrete, or that there is other material, also combustible material at the ceiling. That might be a problem too, because if you have combustible material at the ceiling, then that also could be ignited by a car fire, and then the fire spread will be much more faster than only the fire spread from car to car. So that's okay. So then I think maybe I can also the spreadsheet that I showed you. I can also upload that. Yeah, I can also upload that with a handout of the workshop, or I can email. I don't know what the strategy of IFE is for the handouts. If it's only the handout of that, I can also add some material to that, and then I can also add you the spreadsheet, and you can use it, you can try it. But if you do, then I want your feedback, please. So then email your feedback, and so we can maybe do some. We can make the method better or more robust or whatever. But if you have some suggestions, some questions, you can always email me. Questions you can also ask me afterwards. No, whatever. Are there any questions left? No? No, all longing for a drink. Okay, then we keep it by this. Thank you.